Alright guys, so today we're going to be talking about concavity. And so what is concavity? So recall that last time, or the few times before rather, we were talking about functions that say look something like this. And we had that at this point the function went from decreasing here on left hand side to increasing on the right hand side of that critical number, and that was characterized by the derivative being either positive or the derivative being negative. So now we're going to think about as to what happens when the second derivative is positive and when the second derivative is negative. So let me redraw this. I'm going to take a look at a function that has both behaviors together so we can describe it. And then once we have that, we will introduce our official definition for it. All right, so our function now is going to be a little bit more interesting. It's going to say look like this. And I'm going to grab a different point that at the moment will not be very clear as to why I'm picking this point. And I'm going to separate my interval on this left part of the interval, or left hand side of the real line I should say rather, and then the right hand side of the real line, separating at this point that at the moment I'm just going to call C, and it's not very clear as to why I care about it. So let's take a look at what happens to the second derivative here. And to do that, what I'm going to be looking at is what happens to the derivative first. So in this case, the function is increasing, so I have a tangent right here, and it seems to be pretty steep, the tangent, so the first derivative will be positive, and it'll be somewhat large in absolute value. Well, it's positive, so it's definitely going to be positive in absolute value. Let's grab this one right here, and you see this slope is larger than this one here, right? And then here then becomes almost 0. At some point in the critical number becomes 0, and it starts becoming the negative. So if I were to draw what happens to the first derivative here, I started with a positive number that was somewhat large. Let's say somewhere here. Then I went down to another positive number, but it was a little bit smaller. So let's say here. At some point around here, close enough, we went down to 0. And then we became negative down here. So if you see what's happening to my derivative, if I plot it, the graph of the derivative is decreasing. So if the derivative is decreasing, whenever you have a function that is decreasing, what do you have that the second derivative is? So if its derivative, also known as f double prime, is negative. So right here, you see that the function has this behavior where if you were to put water up here, the water would roll to either side of this. It would not accumulate. That we will call is concave down, or simply concave. So the function is concave, and when the function is concave, the derivative is decreasing, meaning its second derivative is negative. So on this interval here, my second derivative is negative. Now let's move on to this point that I put somewhere here. And let's see what happens to the derivative of this function again. So at this point, nothing special, it's still negative, somewhere here, let's say. But if you see what's going to happen to your derivative, it's going to start going from negative, slightly less negative, 0, positive, even more positive. So what that means is that starting here, the derivative starts turning, you hit 0 around here, and you keep growing. So what does that tell you is that when the derivative became increasing, that is, the second derivative became positive, you had a change in the behavior. Now the function is concave up. This is what I call concave up, that if you were to put water in it, it would accumulate here. So this is concave up. It holds water, if you will. So this right here is going to be the case when you have concavity up. So now if the derivative is increasing, now we're on this other interval. The derivative f double prime is positive. Now there is another way to do this mathematically. So you say that on an interval the function is going to be concave, or concave down is what we call, if its secant line between any 2 points, say there, a little dark that point, but let's say that line there, the secant line between any 2 points on that interval is below the curve itself, that we call it then is concave. Or concave down is what we're going to call it. Now the function is said to be convex if the secant line on an interval, if the secant line is above the curve on that interval. But we're not going to call it convex and concave, we're going to call it concave down and concave up. That's a little bit easier to remember. You don't have to be thinking about which one was convex, which one is concave. We're just going to call it concave down, concave up. So let's go ahead and write our theorem that will help us characterize the concavity. But this is the explanation. This is all you needed to understand that whenever the second derivative is negative, your function is going to be concave down. When your second derivative is positive, your function is going to be concave up. So let's write that as a theorem. I think we can still fit it here. If f is second differentiable on an interval AB, so the second differentiable on the open interval, the function f is concave up alternatively down on the interval if and only if the second derivative is positive, alternatively negative, on the interval a to b. So what that will do is it'll give us a way to find or determine the concavity of a function on, or the intervals where a function is concave up or down, just based on this theorem. All right, so with that in mind, let's go ahead and solve a few examples. All right, guys, so let's take a look at this problem here. Discuss the concavity of the function, and we're given this function right here. So our first step will be to take the second derivative. So take the first derivative, you get negative 3x squared by dropping the 3, subtracting 1. Drop the 2 times 3 is 6 times x to the power of 2 minus 1 plus 10. And then normally when we were doing increasing, decreasing, we would stop here and set it equal to 0 or find when it's undefined. But for concavity, you'll do a second derivative before you get to that. So take the second derivative. 2 times 3 is going to be negative 6 here. X2 minus 1 is 1 plus just 6 here. And that's that. The derivative of 10 is 0. So we set this equal to 0. And we solve. So firstly, we can factor a 6 out of that. Or let's just subtract 6 on both sides. Probably easier to do it that way. We get negative 6 equals negative 6x. We divide by negative 6 on both sides, and we get x equals to 1. So that's going to be the point where the concavity could change. So what we're going to do is the same thing we did for the first derivative test. We're going to grab the real line, and we will separate it out at our now possible point where the concavity changes. By the way, a point where the concavity changes of a in a graph, or the point where the concavity changes, is called the inflection point. So this right here is a possible point of inflection. We pick that value and we separate our line into intervals. So from negative infinity to positive 1, and then from 1 to positive infinity. Now we pick a test value like we did before. So here I'm going to grab, for example, 0, and I'm going to grab 2 over here. We're going to look at the sign of, this should look familiar already, because it looks the same as our first derivative test, except now we're using the second derivative. So we're going to evaluate the, or look up the sign of the second derivative. So we plug 0 here, we get positive 6, gives me a positive value. And then when I do evaluate it at 2, I get negative 6 times 2, which is negative 12, plus 6 is negative 6, which is negative. Remember, we don't care about the number, we care about the sign only. Our conclusion then would be, or concavity, if you will. You can write that concavity. Here's going to be concave up. Here's going to be concave down. And I'm just going to give you a little bit of an idea as to what the graph of this function looks like. It's not going to be perfect, but just so you have an idea. So at 1, and the point is 1, negative 12, so let's grab it somewhere here. There's where your concavity will change. Before that, the function will be doing something like this. And then here, changes concavity and becomes concave down. And the graph will be doing something along those lines. So you see here, the graph of the function is concave up. And then past this point of inflection, now we can say it's a point of inflection because it went from concave up to concave down. Concavity did change, so we can say it's a point of inflection, not just possible, but actually a point of inflection. We know that the function went from concave up to concave down, and so we have that right there. All right, let's do another example with a polynomial, and then we'll do one with a rational function, and I think that's what we're going to do for today. All right, guys, so we're going to go ahead and look at this problem here, and again, our first step is to find the second derivative. So we start with the first derivative. We get negative 4 divided by 12 and then 3 and then you say, why don't you simplify it? Because it will cancel out in the end. So I'm going to go ahead and do it now. Take my second derivative. And I get 3 times 4, or negative 4, so negative 12. And then, of course, there's a square here. 3 minus 1, 2. Then this one gets me a 2 times 3, which is 6. And then a 2 from this one. So we have that. Notice how nice that this all simplifies. And I usually prefer, whenever I'm going to solve something equal to 0, and in fact, let me set it equal to 0 here, just to save one line. I usually like to multiply everything times -1, so my leading coefficient is positive. I just like factoring that way. And with that, then I get the equation 0 equals x minus 2, x plus 1, from where I get two possible points of inflection when x minus 2 is equal to 0, which gives me x equals to 2, or when x plus 1 is equal to 0, where I get x equals to -1. I want to put my possible points of inflection on my line in order to draw or write down my intervals. So -1, +2, I'm going to put them apart so that I can actually fit my intervals. -infinity to -1, -1 to 2, 2 to infinity. So now all I have to do is pick test values. So in between these two guys I have 0, for example. I can pick 3 over here and perhaps -2 over here. These values are completely arbitrary. As long as they're inside of the interval, they are good. And here I needed to write intervals. The next row is the test value, so let me fix that real quick. My intervals, my test values. I put them there, -2, 0, and 3. And then I need to look at the sign of the second derivative. Not the first, but the second. So as before, once you have your derivative factored, or second derivative in this case, it probably would be more convenient to write it in factor form. Like so. Why? Because for you to evaluate the signs, this is way more convenient than this expression here, even. Because then you have to do squares, and this is a lot faster. So if you plug -2 here, you get -2 minus 2 is -4. -2 plus 1 is -1. When you multiply them, you have negative times negative is positive. I'm going to write it just so that we don't get in the habit of doing it in our heads. So at x equals to -2, I'm getting -2 minus 2 times -2 plus 1. So when you compute that, that's going to be -4 times -1 plus 1, which is -1. So negative times negative, that part is positive, times negative again, we get that the sign is negative. I may have said positive. I may have forgotten this negative. So good thing I wrote it, you see? All right. So at 0, that's the one where it's a lot easier to evaluate it in this form. Because you plug 0 here, you get 0 plus 0 plus 2, it's +2. That one we really don't need to do it in this form. You can, of course, evaluate it if you so prefer, but I think that one is easier to just plug directly and get your y-intercept there. So that's probably easier. So at x equals to -1, not -1, +3. I'm fighting with myself here. I was looking up here and I thought about the -1. I have to remember this is the 3 I'm evaluating. So at x equals to 3, I get -3 minus 2 times 3 plus 1, from where I get 3 minus 2 is 1, 3 plus 1 is 4. This is positive times negative, it's negative. And again, another word of caution. Even though we have alternating signs, remember, this not always has to be the case. It will not always be the case, so please evaluate them nonetheless. So my conclusion here is that the function is concave down between -infinity and -1, also down from 2 to infinity, and it is up from -1 to 2. And the graph of that function, I'm going to just sketch it. You can graph it on a graphing program. So at -1 and then 2, the function will be doing something more or less like, it's a little bit before that, changes concavity there, has a relative minimum at 0, and then starts going up, and here changes concavity where it then goes down like that. That's a good idea of what the graph will be doing. Of course, it's not drawn to scale, but it gives you an idea what the concavity will be. It's going to be concave down here. Here's your point of inflection, changes to concave up. Here's your point of inflection, changes to concave down again. So that's sort of what the graph will be doing. So we will do one more just for a rational function, because I do want you to take one more thing into consideration. With rational functions, we have vertical asymptotes. I want you to look at those. So let's do one more, and then we'll finish the video there. All right, guys, since the video was starting to get a little bit long, I went ahead and computed the two derivatives for you so we can save a little bit of time, but please go ahead and compute them, pause the video, make sure that you get the same result. But we're going to be looking at a rational function, and there's something special about, or something extra that you have to consider when you're doing a rational function. Because notice that here, I can look at the point where the second derivative becomes 0 to find possible points of inflection, but there's no zeros for this function. So there's no solution to this equation. So a priori, there's no possible points of inflection. However, notice that you have at x equals to 4, you have an asymptote, a vertical asymptote. And it is an asymptote for the original function. Even though that would not be a point of inflection, the concavity can change. And it will change when you go through that point. So when you're going to make your table, I told you put your possible points of inflection. But when you're talking about rational functions, or functions that can have an asymptote, such as the tangent, cotangent, still include your asymptotes as well. So here there is no possible point of inflection from the second derivative being 0, but we do have that 4 provides us a point, not a point on the graph, but a point on the x-axis that will partition the interval, and to the left of that interval it will have one concavity, and to the right it will have another. So be mindful of that. So from negative infinity to 4, and then from 4 to infinity, we'll pick test values. So in this case, I'm going to graph 0 here and 5. We'll look at the sign of the second derivative, and notice that the only thing I have to check is this expression here. So at 0, I have that the second derivative will be negative 2 over negative 4 cubed. The cube respects the sign, so you'll have a negative number in the denominator. So negative times negative, it will be positive. You can also put in your calculator, but I suggest that you practice this because it's easier to get the signs like that. So 5, when you plug 5 in here, you get 5 minus 4 is positive, times negative, negative. So the function will be concave up prior to the vertical asymptote, and it's going to be concave down when you pass that vertical asymptote. And the graph of this function is going to be something like this. You'll have a horizontal asymptote at negative 1. You're going to have a vertical asymptote at x equals to 4, say somewhere here. You have an intercept at x equals to 3. So let's say here. And the graph will do something like this. You have a vertical asymptote there. And then you have a vertical asymptote here. And you see you have concave up, as it was predicted by our table. And you have concave down, as we had computed there. All right, guys, so that's going to be where we're going to stop for this video, and I'll see you next time.